Okay, this is the first part of this homework for the chapters on Lenz's law and AC circuits. In this figure, the magnetic field through the loop changes according to this function, this B 6t squared plus 7t, where B is in Tesla and t is in seconds. The radius of the loop is 1.5 centimeters and the resistor is 3 ohms. What is the magnitude of the EMF and what is the magnitude and the direction of the current? Okay, so first I need to find the area, so let's just go ahead and do that. So to find my area of this loop, it's equal to pi r squared. That's equal to pi times the radius, which is 1.5 centimeters, or 0.015 meters. That is equal to, let's see, 0.0007 square meters. All right, I also need to find dB dt, because I'm looking for EMF. Let me just sort of show you the big picture. I'm looking for EMF, which by Faraday's law is equal to the negative of the change in the flux in time. But remember that flux is equal to B times A. It's actually the dot product of B and A. So this d phi is going to equal to negative A dB dt. So I have A here. Now I need to find dB dt. dB dt, that's going to be the derivative of this function, which is going to be 12t plus 7. Notice that at all times that this is a positive function. That tells me this function has a positive value, excuse me. So that means that the magnetic field is increasing. That would be important when we find the direction. Right, so I can come down here and put these values in. I'm looking for it at 2 seconds, but let me just first put in my A. A was 0.0007 square meters, and then dB dt is going to be 12 times 2 seconds plus 7, and that has a value equal to 0.022. It's actually negative 0.022, but the negative just tells us the direction, and we need to use our right-hand rule and Lenz's law in order to determine the direction. So the EMF is 0.022 volts. That's the EMF provided by this changing magnetic field. Now we want to find the direction. So the magnitude of the EMF is 0.022 volts. Now I want to know the magnitude and the direction of the current. Well, let's see, the magnitude is easy. I have 3 ohms here, so I is equal to EMF over the resistance, so it's just 0.022 volts over 3 ohms. I don't have that written down, so let's see, 0.022 divided by 3 is 0.007 amps. Now I want to find the direction of it. That's the magnitude of that current. Now notice here that my magnetic field is into the page and it's increasing. So my magnetic field is in the negative K direction. Right. The magnetic field that is induced, or rather the current that is induced, will cause a magnetic field that opposes this. Because it's increasing, the magnetic field that's induced, I'm going to call this B induced, is going to be in the positive K direction. So my induced magnetic field in this coil of wire that's generated by this coil of wire is going to be the opposite direction of this increasing magnetic field. Go back to your notes on Lenz's law. We use Lenz's law to find the direction of this induced magnetic field. And then we do our right-hand rule like we had in the previous chapter on magnetic fields. We let our thumb go in the direction of the current in this loop, and our fingers give the direction of the magnetic field. So my current is going to flow in this direction. So it's going to be 0.007 amps in the counterclockwise direction. All right, step back through that. I want to find the EMF by Faraday's law. It's the equal to the change in the magnetic flux with respect to time. And to find that, we say the area times the magnetic field. Remember, magnetic flux is B dot A. In this case, B and A are both, well, let's see, they're parallel. So that cross product is just equal to A times B. And then I had to take the derivative of B with respect to t to find this function, and then plug in 2 seconds, and then I find my EMF. That's the magnitude of my EMF. And then I have to use Lenz's law to find the direction of this induced magnetic field. This is the magnetic field that's caused by the induced current in the loop of wire. So there is a current that's induced in this direction, in the counterclockwise direction, that causes this magnetic field that comes out of the page in the plus K direction. And that's how I determine this direction for the current. A square wire loop with 2 meter sides is perpendicular to the magnetic field as shown. 1/2 of the loop is in the B field, which varies with time according to this function, and the loop contains an ideal battery with equal 20 volts. What is the net EMF and the magnitude and the direction of the current? Let's see. I'm going to actually put in a resistance here, or let's say that the resistance of the wire is 2 ohms. The resistance for 1 turn of the wire is 2 ohms, and then we'll go from there. This is a little bit different because if you want to find the magnitude of the current, if there's no resistance, then your current is it's infinite, basically, right? So we have to have some amount of resistance. Okay, so just like we did before, we're looking for the EMF that's induced. To find that induced EMF, that's equal to negative d phi dt. So we need to find out how is this magnetic field, or how is this magnetic flux given by phi changing with time, and then that will equal to our EMF, our induced EMF. And once again, don't worry about this negative. In fact, I just won't even write it because that just has to do with the direction of the EMF, and we'll find that by looking at the at Lenz's law. Okay, so first thing I do is I know that phi is equal to B dot A. These are all vector quantities. B here is in the plus K direction, and A is also in the plus K direction. Remember, the A vector, the area vector, is a vector that comes out perpendicular to your shape. So here, as long as they're parallel or anti-parallel, then your dot product won't have that cosine theta term in it. All right, so I need to find my area. My area is the area of this square that's within the magnetic field. So I had a square that's 2 meters by 2 meters. So the area of the whole square is 4 square meters. And it's going to be 1/2 of that. 1/2 of 2 meters times 2 meters. Or you can think of it as the area of that triangle, which is 1/2 base times height. And that's just equal to 2 square meters. All right, so that's my area. Now I also need to find out what is my magnetic field, how is it changing with time, and I'm looking at a particular time. Well, let's see, what is my particular time? Oh, no, we'll see. So here my BT is this function, 0.0420 minus 0.087. If I take the derivative of that, I'm just going to get minus 0.87. So the magnetic field is changing at a constant rate that's equal to this negative 0.87. Notice here that the magnetic field is actually decreasing, which will be an important fact later when we actually find the direction. But let's go ahead and calculate the magnitude of the induced EMF. That induced EMF is equal to d phi dt. That's going to equal to A times dB dt. Remember, this term is my d phi. A times B is equal to my magnetic flux. So that's going to be 2 meters squared times negative 0.87. Actually, I'm just going to call it positive because I'm just looking for magnitudes here. And 2 times 0.87 is equal to 1.7 volts. All right, so that is the the magnitude of the induced EMF. Now I need to find out what is the direction of that EMF. Let me clean this up just a little bit. I don't need this triangle anymore. Let's do it to a different color. Red is kind of harsh. All right, so I'm looking. I know that I have this 1.7 volts, but I don't know which direction it's in, so I need to find the direction. Let's go back to this idea that the magnetic flux was decreasing. That means that the flux is also decreasing in magnitude. So, by Lenz's law, the induced B field is in the direction same direction as the originating B field. Look back at that Lenz's law, we had 4 different cases. All right, and in this case, I have a decreasing magnetic field. The magnetic field that's drawn here is decreasing, so the induced magnetic field is going to be in the same direction. All right, this is my induced magnetic field. Now, in order to induce a magnetic field like that, the EMF that's generated in this loop of wire is in that direction, in the counterclockwise direction. So this EMF drives a current in the counterclockwise direction, which I could represent this as another battery, if you would, by drawing a battery that looks like this. So these 2 batteries are both oriented in the same direction. That means that my net EMF, say I have the induced EMF, which is 1.7 volts, in the same direction as the other EMF, which is 20 volts. So my net EMF is going to be 22 volts, 21.7 or 22 volts. All right, so that's the first part of the question. What is the net EMF? That's 22 volts. Now let's find the magnitude and direction of the current. And as I said, we're just going to pick one turn is 2 ohms, let's say. That means that the current is the EMF over the resistance. That's going to be 22 volts over the resistance, which is 2 ohms or 11 amps. So that's my current in this wire. I have part of the current that's induced by the changing magnetic field and part of the current that's just caused by the battery that's operating in the circuit. Now what happens if I go to 10 turns of wire? Well, if I have 10 turns of wire, this increases by a factor of n. All right, so I'm going to have not 1.7, but now I will have 17 volts. So instead of 22, I will have 37 volts. All right, so when I calculate my new current, it will be 37 volts divided by 20 ohms, because I also increased this, the resistance, by a factor of 10, because where I had one loop had 2 ohms of resistance, 10 loops will have 20 ohms of resistance. And I get a current that's equal to 1.85, or we'll call it just 2 amps. All right, so a couple of things you have to account for. You have to account for the changing magnetic flux here, because I increase this by a factor of n if I have 10 turns. That causes for a greater induced EMF, but it also causes for a greater resistance. Now, in practice, these coils have a very, very small resistance, so you would actually get a much greater current, right, because your resistance would not increase that much. All right, what is the magnetic flux through the loop shown in this figure? So remember, magnetic flux, that's this phi, is equal to B dot dA. So if I imagine this area, I have this area right here. The area vector will have a direction in the plus k direction. it acts perpendicular to the area that you're looking at. But actually notice here that I have two different areas. I need to consider this section separately because the magnetic field is different, and this section separately because the magnetic field is different. Alright, so let's do this one first. I have B dot dA, taking the cross product of that, is equal to 2K, that's my magnetic field, dotted with the area. And if I have a 10 centimeter by 10 centimeter square, which is what I have, that has an area equal to 0.1 meters squared. And 0.1 meters squared is equal to, 0.01. All right, so I have 2 times 0.01 square meters in the positive k direction. K dot k is equal to 1, so this is 0.02 Webers. Now, if I want to do the second section, so looking at this section now, I come over here and my B dot dA for this section is equal to, again, negative 1K. That's my magnetic field, dotted with 0.01 meters squared in the positive k direction. So that gives me a magnetic flux equal to negative 0.01 Webers. Now I just add those up because I want to know the magnetic flux through that total loop. So if I bring these two together, of course, I'll just do positive 0.02 plus negative 0.01, and of course that's equal to positive 0.01 Webers. So that's my net magnetic flux, just the sum of those individual magnetic fluxes. Okay, let's see. We have an LR circuit. First of all, I just want to know what is the equilibrium current. That should be really simple. It's 6 amps. Hopefully it's simple. Hold on just a second.